Quantum mechanics is difficult to learn, both because of the many counterintuitive physical manifestations and because of the sophisticated mathematical apparatus. However, the advent of computers and specialized symbolic computing programs can ease the mass, allowing effort to be channeled toward physical understanding. Using few code lines that embed usual formulae, we can visualize the phenomenon or generate complex solutions in terms of special functions. In the following, we will use Wolfram Mathematica. Anyway, after modeling the phenomenon through computer-aided study, it is advisable to return to the classic textbook, which will now seem much more natural and easy to understand. Here we will perform quantum mechanics calculations in the Schrödinger wave representation. We will first study the wave as a form of propagation in space of an oscillation. Oscillations occur in all systems removed from a stable equilibrium position. In such systems, the potential energy depends on the position. We can develop the potential energy in the Taylor series around the equilibrium position x0. From classical field theory, it is known that in conservative systems there is a force given by the partial derivative of the energy with respect to the position. The minus sign is necessary for a stable equilibrium where a force in the opposite direction of movement occurs. Let's take the origin in the equilibrium position, where the first derivative of the energy must be zero. In Newtonian mechanics, the force is also proportional to the second derivative of the displacement with respect to time. So we may equate these two forms using a positive proportionality constant c. To be sure that the proportionality constant c is positive, we will rename it as omega squared. Mathematica can easily solve this differential equation. We may also specify some initial conditions. This is a well-known solution for a localized harmonic oscillation. We can make an animated graphical representation of a localized oscillation. In many cases, oscillations can propagate in the form of waves. First, let's clear the previous variables. Let us consider the simplest case in which the propagation is made along a single axis, x. Of course, if the wave velocity is finite, v, a delay will occur x over v. We must consider the retarded time t minus x over v. We obtain a general form of the wave function. Let us deduce the equation of a one-dimensional wave. The second derivative of the wave function with respect to time. Now the second derivative of the wave function with respect to space. By comparing these two expressions, we may write the wave equation. This is a partial derivative equation that may be solved using the separation of variables method. Unfortunately, Mathematica does not yet know how to do this directly, so we have to manually factorize the function of two variables. A little bit of algebra allows us to rewrite the equation so that each of two variables occurs on a different side of the equation. Now both the left and right sides of the equation depend on a single variable. Both must be equal to a constant. Otherwise, if for example t varies and the right side varies, the left side does not depend on t and there will be no equality. So the right side must be constant. The same happens if x varies. Hence, the left side must be also constant. We saw earlier that the right side is minus omega squared, so this is a constant. We may also impose some initial conditions. It is convenient to express the wave function in an exponential form. Let's introduce some more common notations in the field of waves. Omega is the angular frequency, while t is the period. The product Vt is a wavelength, lambda. We may also define the wave number, k. So we may write the wave function in the exponential form. we notice that there are terms with the same sign and terms with the opposite sign for x and t. We choose the positive sign for x according to the usual orientation of the x-axis. We verify that such a linear combination satisfies the general wave equation. So we calculate the difference of the two members and it gives 0. So this equation is satisfied. So there are two terms of the wave function which correspond to the two directions of propagation, as we will see. We may consider this term as a progressive wave. We may graphically represent the real part of this wave function and the real part of the second term as a regressive wave. Let's make some animation to represent these two waves. This is a progressive wave propagating to the right. This is a source of oscillation in the origin x equals 0. Progressive wave a regressive wave. We can visualize the wavefront by multiplying the wave function with the proper Heaviside function. We can visualize both waves simultaneously. We will encounter cases in which, in a region of space, there are waves in both directions with the same frequency and constant phases. In a linear space, they interfere by addition and give rise to a stationary wave. Progressive wave, regressive wave, stationary wave.